Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at the inverse trigonometric forms of integration. Instead of just jumping in and giving you what the forms are, I'm going to show you where they came from. So I want to start by letting y equal an inverse sine, and I don't want it just to be of u, I want it to be of the function u divided by the constant a. So a is a constant and u is a function of x. We're going to start off by differentiating this because we know how to find the derivative of an inverse sine function. So it will be 1 over the square root of 1 minus this function, except now it's u over a squared, then times the derivative of this. So using the chain rule, now when I differentiate u over a, which is the same as 1 over a times u, the derivative will be 1 over a, the constant, times the derivative of the function. The derivative of u with respect to x is du dx. Now I want to simplify this. To combine these terms, I need a common denominator. So this will be a squared over a squared minus u squared over a squared. I'm going to combine these fractions, and I'm also going to multiply both sides by dx. And what I'm going to do next is break up the square root. So it'll be the square root of a squared minus u squared over the square root of a squared, which is just a. And if I take 1 over this, I can write that as the reciprocal. So it will be a over square root of a squared minus u squared. And the a's will cancel. Now I'm going to integrate both sides. So that will be y equals this integral. I'm going to reverse that. And I already know what y is equal to. So therefore, we can say that the integral of 1 over square root of a squared minus u squared du is equal to inverse sine of u over a. And remember, we could have a constant. That is one of our inverse trigonometric forms for integration. Let's take a look at an example. If I had this integral, if we were to fit it in this pattern, a squared is 16, so a is 4. U squared is x squared, therefore u is x, therefore du is dx. You can see that we don't have to do any manipulation, it fits the pattern as is, so we just integrate it by plugging into this pattern. So this integral will be the inverse sine of u, which is x, over a, which is 4. Plus a constant of integration. Let's do another example. A squared doesn't have to be a perfect square. So if a squared is 5, that means a is square root of 5. And u squared, in this case, is 4x squared. So u will be 2x. So the du factor will be 2 dx. So we need a 2 in our numerator. If we multiply by 2, we also have to divide by 2. Now it fits this pattern. So we can integrate. It will be 1/2 inverse sine of u, which is 2x, over a, which is square root of 5. And we're done. The derivative of inverse cos is almost the same as this, but it's negative. So we don't need to take that as another pattern, but we do have to look at the inverse tan pattern. So this time we're going to let y equal the inverse tan of u over a. Again, u is our function of x, a is a constant. We're going to differentiate this, and we learned previously that the derivative of an inverse tan function was 1 over 1 plus the function squared times the derivative of the function. So the derivative of u over a, which is the same as 1 over a times u, the derivative of that will be 1 over a times the derivative of u. We're going to simplify this, I'm also going to multiply both sides by dx. So I'm going to have dy equal to 1 over, we need a common denominator to combine these terms. So 1 is equal to a squared over a squared plus u squared over a squared times 1 over a times du. I have a common denominator, so I can combine those. 1 over this, now I can take the reciprocal, and one of the a's will cancel. So I'll have dy equal to a over a squared plus u squared du. Let's integrate both sides. The integral of dy is simply y. Let's reverse this. I'm going to pull an a out in front of the integral sign. I can do that because it's a constant. So a times the integral of 1 over a squared plus u squared du is equal to y is inverse tan of u over a. Therefore, I can say that the integral of 1 over a squared plus u squared du is equal to 1 divided by a. I'm just going to divide both sides by a times the inverse tan of u over a. So that's another important inverse trig form that we can use when we're integrating. Let's take a look at some examples. We're going to plug into this pattern. We have a squared equals 25. Therefore, a is equal to 5. We have u squared equal to x squared. Therefore, u is equal to x. Therefore, du is dx. So I don't have to do any manipulation. It fits my pattern. My integral will be 1 over a, so 1 over 5, times the inverse tan of u, which is x, over a, which is 5, plus c. So a squared is 7. So a is square root of 7. U squared is 9x squared. So u is equal to 3x. So the du factor is 3dx. I have that. I don't have to do any manipulation. I can plug into my pattern. My integral will be 1 over a, so 1 over root 7, times the inverse tan of u, which is 3x, over a, which is root 7, plus my constant of integration. Some of these questions are a little trickier and you have to do a little bit of manipulation. So let's take a look at some of those. Sometimes you'll see an example that doesn't look like it fits our pattern at all. However, if you remember completing the square, if you have an expression like x squared plus 2x, if you want to make this a perfect square, you take this coefficient, you divide by 2, and you square it. So 2 divided by 2 is 1, we square it, is a 1. If you add that, this is now a perfect square, and it can be factored into x plus 1 squared. So what we're going to do is see if we can get a perfect square in this denominator. Can we break 10 into 1 plus something? We can write 10 as 1 plus 9. Now, this is a perfect square. So I write it as x plus 1 squared. Now it looks like it might fit this pattern, where u squared is x plus 1 squared. So u is x plus 1. Du will be dx. A squared is 9, so a is 3. So we don't need to do any manipulation. We can integrate this according to this pattern. So this integral will be equal to 1 over a, so 1 over 3, times inverse tan of u, which is x plus 1, over a, which is 3, plus c. So you may encounter questions where you do have to complete the square and break up your constant, like I did here. Let's look at one more example. Here we have a question that does not look like it fits this pattern, but we have no way of integrating the way it sits, so we have to get creative. And what we're going to do here is we're going to break up that numerator. So I'm going to write this as 2x over 4x squared plus 9 minus 7 over 4x squared plus 9. I'm going to be able to integrate each of these terms, but I'm going to be using a separate pattern. So I want to break up these integrals. I'll pull the 2 out front, and I'll have the integral of x over 4x squared plus 9 dx minus, I'll pull the 7 out front on this integral, and I'll have 1 over 4x squared plus 9 dx. Because I have a factor of x here, this is actually going to follow my basic log form. So what I'm going to do is I'm going to write that as 2 times the integral of 1 over 4x squared plus 9 x dx minus 7 times the integral of 1 over 4x squared plus 9 dx. So this pattern is going to be 1 over u, where u is 4x squared plus 9. So the du factor is 8x dx. I have the function part of it, I'm just missing the 8. That's not a problem. I multiply by 8, I also divide by 8. Now I have my du factor. I can integrate this. 2/8 is 1/4. The integral of 1 over u du is the natural log of u. Now in this case I don't need to use absolute value signs because 4x squared plus 9 can never be negative. The pattern I'm going to use for this term is my inverse tan pattern. I have 1 over u squared plus a squared. And it doesn't matter the order that I write those. A squared plus u squared is the same as u squared plus a squared. So I'm defining u squared as 4x squared, which means u is 2x, which means du is 2dx. I'm defining a squared as 9, therefore a is 3. I don't have the 2, the factor of 2 that I need, so I'm going to multiply by 2 as long as I divide by 2. Now the pattern is 1 over u squared plus a squared. I have my du factor, so I can plug into this form. It will be 7/2 times 1 over a. 1 over a is 1/3, so that gives me 7/6, times the inverse tan of u, which is 2x, over a, which is 3, and add my constant of integration. So these questions with integration can get very difficult. There's often manipulation involved, as well as recognizing different patterns. And the only way you get good at recognizing patterns is to practice a variety. You're going to see questions that look very similar, but the du factor will make all the difference in what pattern you're going to use. For example, these look very similar, but that factor of x means I can use my general power formula to integrate this, but I can't with this. I need to use my inverse sine pattern. Similarly, I can use my basic log form here because I do have that x, which is part of the du factor. So this I would integrate using the basic log form. However, I don't have the x here, so in this case I would use my inverse tan pattern. Practice, practice, practice. The next technique of integration that I'm going to cover is integration by parts. So when you're ready, I'll see you on the next video.